Hello, Engineer Badana. My name is Anton Earl Elim. I'm here to discuss about the problems. So, problem number one, a centrifugal pump operating under a steady flow condition delivers 600 GPN, 600 gallons per minute of water at 80 degrees Fahrenheit from an initial pressure of 12 psia or 12 pounds per square inch to a final pressure of 40 pounds per square inch. The diameter of the suction inlet to the pump is 6 inch and the diameter of the discharge outlet is in 4 inch. If the suction of the discharge at the same are level and there is no change of internal energy, what is the work in British thermal unit per minute and horsepower and in kilowatts? So here are the given values. So volume flow rate is equals to 600 gallons per minute. So the initial temperature is equals to 80 degrees Fahrenheit. So the initial pressure is equals to 12 pounds per square inch absolute. So the final pressure is equals to 40 pounds per square inch absolute. And the diameter of the inlet is equals to 6 inch and the diameter of the outlet is equals to 4 inch and the density of 1000 kilograms cubic meter. So we have the diameter given, so we can solve for the area. So initial area is equals to pi over 4, the diameter squared. So pi over 4 is equals to 6 inch squared. So the answer would be 9 inch, 9 pi inch squared or 28.27 inch squared. So the cancellation of the units. So in every 1 feet there is 12 inch, the exponent 2 times in every 1 meters there is 3.28 feet, exponent 2. So the initial area would be 0.18 cubic square meter, and the final area is equals to pi over 4 diameter squared. So substitute the given values. Pi over 4 is equals to 4 inch squared, so equals to 4 inch squared or 12.57 squared. So in every 1 feet there is 12 inch. So the exponent 2 times 1 in every 1 meter there is 3.28 feet squared. So the final area would be 8.11 times 10 negative raised to the power of negative 3 square meter. So we have here the conversion of the gallon per minute to cubic meter per second. So 600 gallon per minute. So in every 1 gallon there's 3.78 3.785 liters. In every cubic meter there is 1000 liters, and in every 1 minute there is 60 seconds. So let's cancel the minute. We can cancel the minute, gallon, and the liters. So we have here we have here the final unit of cubic meter per second. So the answer would be 0.0375 cubic meter per second. So to solve for the velocity, we have the volume flow rate. Volume flow velocity is equals to volume flow rate over the area. So initial velocity is equals to volume flow rate over area. So substitute the given values, 0.03785 cubic meter per second over 0.018 square meter. So the initial velocity is equals to 2.07 meters per second. And here the final velocity is equals to 0.03785 cubic meter per second, and here 8.11 times 10 raised to the power of negative 3 square meter. So the final velocity would be 4.77 meters per second. So we can have now the steady flow rate equation. So Q is equals to delta K plus delta K, or change of kinetic energy, plus change of workflow plus work. So transpose work is equals to negative change of kinetic energy minus change of workflow. So the delta K, or change of kinetic energy, is equals to V2 squared minus V1 squared over 2K, the constant K. So 4.77 meters per second squared minus 2.07 meters per second squared over 2 and 1 times 1 kilogram meter per Newton second. So in every 1 kilojoules there is 1000 joules, and cancel meters per second, cancel meters per seconds, cancel the meter, cancel Newton and seconds. So and also the joules here. So we have left the unit kilojoules and kilogram. So the delta K, or change of kinetic energy, is equals to 8.74 times 10 raised to the power of negative 3 kilojoules per kilogram. And here, first we have to convert the PSIA to kPa. So 12 PSIA in every 14.7 pounds per square inch absolute, there is 101.325 kilopascal. So we cancel the PSIA, pounds per square inch absolute, you can cancel it. So we are left with the unit kilopascal. So the answer would be 82.71 kilopascal. So the final pressure 40 PSIA. So we can convert it to kilopascal. In every 14.7 pounds per square inch absolute, there is 101.325 kilopascal. So the answer would be 275.71 kilopascal. And here the change of workflow we can solve now. So the change of workflow is equals to P2 V2 minus P1 V1. So or it is equals to P2 over rho minus P2, or final pressure, over density rho minus initial pressure over rho. So substitute the given values: 275.71 kilopascal over 1000 kilogram per cubic meter minus 82.71 kilopascal over 1000 kilogram per cubic meter. So the change of workflow is equals to 0.193 kilojoules per kilogram. And also we can now solve for the mass flow rate. So mass flow rate is equals to volume flow rate over rho. So substitute the given for values: 0.0375 cubic meter per second times the rho 1000 kilograms per cubic meter. So the mass flow rate would be 37.5 kilograms per second. Okay, you can cancel it. So we have left the, can cancel this and cancel this. So we have left the kilograms and second units. So now we can solve for the work. So work is equals to change of kinetic energy minus change of workflow. So 0.202 kilojoules per kilogram negative times 37.5 kilograms per second. So work is equals to negative 7.57 kilowatts. So now we can convert the kilowatts in horsepower. So the conversion it is, so negative 7.57 kilowatts times in every 1 kilowatt there is 1000 watts times in every 1 horsepower there is 740 watts. So we can cancel the watts here, kilowatts and kilowatts. So we are left with the unit horsepower. So the answer would be negative 10.14 horsepower. And here we can convert horsepower to BTU per minute. So 10.14, negative 10.14 horsepower times in every 42.4 BTU there is 1 minute per horsepower, minute per horsepower. So the answer would be cancel the horsepower on the horsepower. So the answer would be 420 negative 429.97 BTU per minute. So hi sir, I'm done with the problem number 1. So I'm here with the problem number 2. A certain gas at 15 inch of mercury absolute and 19 degrees Fahrenheit occupies 10 cubic feet if the state is changed until the volume is 30 cubic feet and the temperature is 540 degrees Fahrenheit. Determine the final pressure in pounds per square inch absolute. So the given values here, initial pressure is equal to 15 inch of mercury absolute and the initial temperature of 90 degrees Fahrenheit and the initial volume of 10 cubic feet and the final temperature of 540 degrees Fahrenheit and the final volume of 30 cubic feet. So we are asked to find the final pressure. So we have to convert the temperature to absolute temperature. So initial temperature is equals to 90 degrees Fahrenheit plus 460 to make it 550 degrees Rankine. So final temperature is equals to 540 degrees Fahrenheit plus 460 is equals to 100 degrees Rankine. So and also we have to convert the initial pressure. So 15 inch of mercury absolute in every 29.92 inch of mercury absolute there is 14.7 pounds per square inch absolute. So the answer, we can cancel the inch of mercury here, inch of mercury. So the answer would be 7.37 pounds per square inch absolute. So we have here the gas formula. P1 V1 is over T1 and equals to P2 V2 over T2 or and can now transpose. So we are asked to find the final pressure. Final pressure is equals to initial pressure, initial volume times the final temperature over initial temperature times final volume. So substitute the given formula. Final pressure is equals to 7.37 pounds per square inch absolute times 10 cubic feet times 1000 degrees Rankine over 550 degrees Rankine times 30 cubic feet. So we can cancel the cubic feet, Rankine here, and the cubic feet. So we are left with the unit pounds per square inch absolute. So the final pressure would be 4.47 pounds per square inch absolute. So I'm done with the second problem. So I'm here with the third problem. So a perfect gas has a value of R, gas constant, equals to 319.2 joules per kilogram degree Kelvin, and the K value is 1.26. If 120 kilojoules are added to 2.27 kilograms of this gas at a constant pressure when the initial temperature is 32.2 degrees Celsius. Find the final temperature, change of enthalpy, change of internal energy, and the work non-flow. So the given values are K is equals to 1.26, the mass is equals to 2.27 kilograms, the R is or gas constant is equals to 319.2 joules per kilograms degree Kelvin, and the Q is 120 kilowatts or heat, and the initial temperature would be 32.2 degrees Celsius plus 273 to make it in the absolute temperature of the in degree Kelvin. So the initial temperature would be 305.2 degrees Kelvin. So first we have to solve for the final temperature. So we have here the formula Q is equals to mass over constant pressure times constant pressure, parenthesis, final temperature minus initial temperature. So the constant pressure is unknown, so we have to solve for the constant pressure. So constant pressure is equals to K times gas constant over K minus 1. So substitute the given values. 1.26 times 0.3192 joules per kilogram in Kelvin. So in every 1 joules there is 100,000 kilojoules over 1.26 minus 1. So the CP or constant pressure would be 1.5469 kilojoules per kilogram degrees Kelvin. So we can now use the formula Q is equals to mass times constant pressure, parenthesis, final temperature minus final initial temperature. So substitute the given values. 120 kilowatts is equals to 2.27 kilograms times 1.5469 kilojoules per kilograms degree Kelvin, parenthesis, times final temperature minus 305.2. So the answer would be in degree Kelvin. So let's cancel the units. Kilograms, degree Kelvin, kilograms. Let's cancel. So the kilojoules also. Kilojoules here. Can cancel it. So the answer would be the final temperature would be 339.4 degrees Kelvin. So we can for the change of enthalpy, delta H is equals to mass constant pressure times final temperature minus initial temperature is equals to 120 kilojoules. Delta H is equals to heat or Q. So in C, we have to solve for the internal energy. So change of internal energy is equals to mass times constant volume, parenthesis, final temperature minus initial temperature, parenthesis. So constant volume is equals to, first we have to solve for the constant volume is unknown. So constant volume is equals to R over K minus 1. So R is in gas constant. So R is equals to 0.3192 joules per kilogram degrees Kelvin. So in every 1 joules there is 1000 kilojoules over 1.26 minus 1. So the constant volume is equals to 1.2277 kilojoules over kilogram degrees Kelvin. So cancel the joules, and we have here in the left unit. So the change of internal energy, we can use the formula now. So the change of internal energy is equals to mass over times constant volume parenthesis final temperature minus initial temperature. So substitute the given values. So 2.27 kilograms times 1.2277 kilojoules per kilogram degrees Kelvin times 339.4 degrees Kelvin minus 305.2 Kelvin. So cancel the units, Kelvin, kilojoules, kilograms, Kelvin. So we are left with the unit kilojoules. So change of internal energy is equals to 95.3 kilojoules. So we can now solve for the work non-flow. Work non-flow is equals to pressure parenthesis ini final volume minus initial volume, or it is equals to pressure is bracket mass gas constant final temperature over final final pressure minus mass mass gas constant initial temperature over in initial pressure, or it is equals to mass times gas constant parenthesis final temperature minus initial temperature. So work done flow is equals to mass times gas constant parenthesis final temperature minus initial temperature. So substitute the given values 2.27 kilograms times 0.3192 joules per kilogram degrees Kelvin. So in every 1 joules there is 1000 kilojoules times 339.4 degrees Kelvin minus 305.2 Kelvin. So the work non-flow is equals to 24.78 kilojoules. Thank you, sir. Engineer Balana. Merry Christmas and advance Happy New Year. Thank you.